Today we're basically going to be going through the chemistry, unit 1 of the atomic structure. We're going through your A-level, AQA chemistry, and we will be going through unit 1. It's easy if I show you in the textbook, sorry. We'll be going through the whole of unit 1, which is all of this, unit 2, until there, and then unit 3. So basically, I will be going through your revision guide in detail because I feel like it is pretty useful, and I'll be going through these online notes which I found from ChemRevise. So without any further ado, let's begin. So this first topic is unit 1, of course, and the first subtopic is your atomic structure. So let me go to the atomic structure section in here just to get prepared. Perfect. So, atomic structure. So, details of 3 subatomic fundamental particles. So, there's 3 different fundamental subatomic particles in your nucleus. There's 2 different subatomic particles in your nucleus. You have your proton, your neutron, and you have the electron in your orbital, so your electron shells. So, you can clearly see your protons in your nucleus, your neutrons in your nucleus, and your electrons in your orbitals. So what does that look like? So I'm gonna try to whiz through this because this is actually basic knowledge. So this is your nucleus, of course. You have your protons here, your neutrons here. Protons are positive charge, your neutrons have no charge, and lastly these are your orbitals or your electron shells, which have electrons, which have a negative charge. So your proton is, the position of your proton is in the nucleus. It has relative mass of 1 and it has a relative charge of +1. Your neutron is in the nucleus, has relative mass of 1 and it has relative charge as 0. Lastly, your electron is in your orbitals. Obviously those are your orbitals or electron shells. The relative mass is actually 1 over 1840. I think in GCSE they wanted you to know 1 over 2000, but it's best that you know in A level that you know it's 1 over 1840 because it's just better. And lastly, your relative charge is -1. So the charge on your proton, of course, is +1. Charge on electron is -1. Charge on neutron is 0. Relative mass on your proton is 1. Relative mass on your neutron is 1. And relative mass on your electron is 1 over 1840. So relative mass is basically just the mass of your electron or your proton or your neutron. I don't know why they call it relative mass. They literally just could have called it mass, but they want to be extra like that. So let me just draw a small... let me just quickly write this stuff down. Type it down. So we have 3 subatomic particles found in our atom. We have your proton, your neutron, and your electron. So your proton is found in your nucleus I should write out sentences because it would be easier, because I haven't really made a proper table, did I? No, I did not. So let me just write into small discrete sentences so it's easier to remember and easier to understand. So your proton is found let me fix everything up. So your proton is found in your nucleus. So your proton is found in your nucleus and has a relative mass of 1 and a relative charge of 0. Sorry, relative charge of +1. I don't know why I said 0. Okay. By the way, my laptop's a bit weird, yeah. So I might be typing and suddenly it will move my cursor to there. I don't know why. I think I've used it too much. That's why. So then your neutron is found in your nucleus, of course. Neutron is found in your nucleus and has a relative mass of 1 and a relative charge of 0. First of all, I would like to apologize for my spelling mistakes and other stuff like my punctuation and grammar, but at the end of the day, that's not really important. It's more that you guys understand, and it's more that I'm able to transfer the knowledge and transfer the knowledge and explain it properly to you guys. So how I type, if I make typos, if I use if I use text language basically, then don't worry, I'm not dyslexic. I'm just trying to speed things up. So lastly is your electron is found in your orbitals and has a relative mass of 1 over 1840 and a relative charge of -1. Now I know I said 1 over 1200, which was taught in GCSEs, but I would advise you to remember 1 over 1840 because it's just more, it just sounds more A-level-ish, if that makes sense. So I'm trying to whiz through this because it's actually pretty basics, and I don't wanna focus on this too much. Anyway, so an atom of lithium can be represented as follows. So your mass number is 7 and your atomic number is 3. There's your lithium and there's atomic symbol, which is Li. So the atomic number Z is the number of protons in the nucleus. So atomic number is Z. So the atomic number, which is basically Z, is the number of protons in the nucleus. The mass number is the total numbers of protons and neutrons found in the nucleus. So usually the amount of protons equals the amount of electrons. So if you want to find your electron number, you look at your atomic number and you're like, okay, your proton number is 3, therefore your electron number is also going to be 3. Your mass number is obviously your neutron plus your proton. So if you want to find your proton number, you just minus your atomic number from your mass number to get your neutron number, which in this case is 4. So I hope that's understandable. If it's not understandable, I'll just go here and you can literally just pause the video and try to understand this whole thing. What is very important is that, not very important, but what I find very useful is that they actually use a similar example of lithium in these notes as well as this. So I just like that. I don't know why. Anyways, so isotopes. So isotopes are atoms with the same number of protons but different number of neutrons. Interesting. So your isotopes. So isotopes are atoms. Oh, just completely spelled that wrong. So isotopes are atoms with the same number of electrons. Same number of protons. Wait, am I saying this right? Sorry. So isotopes are atoms with the same number of protons but different number of neutrons. A different number of neutrons. So most probably they will want you to know the 3 different types of hydrogens for your isotope to remember it, because that's how they show in physics. So I'll just show you that example. So the 3 hydrogens, I forgot the name of them. 3 hydrogens are basically your isotopes. What? Why am I on Yahoo? Your 3 isotopes. 3 isotopes of hydrogen. Yep. So it's your protium, your deuterium, and your tritium. So basically, what's your this is a bad quality photo, apologize. So basically, the whole, let me move to this one, I'm sorry, that's annoying me a lot. Basically, your definition of isotope is an atom with the same number of protons but a different number of neutrons. So as you can see, your atomic number actually increases. So 1, 2, 3. Now I know I don't think it calls atomic number here. It calls it a mass number. Sorry, it's a nucleon number. I don't know why I called it atomic number. So basically, the top number and the bottom number have many different names. I refer to the top number as the nucleon number, and I refer to the bottom number as the proton number because that's the easiest for me. If you want to refer using this way, I do get confused with this, but that's a mass number and then that's the atomic number. I don't like to call it a mass number because your mass number is is that, and it's not really that. So it's tedious stuff, which I am mentioning, but it's just life, okay. Anyways, so your protium, the nuclear number of your protium is 1. Then your deuterium, the nuclear number has changed to 2. Therefore, it's an isotope of the same atom with the same number of protons but different number of neutrons. So protium actually has no neutrons at all. Deuterium has 1 neutron, and then tritium has 3 neutrons. So I hope that's understandable. So this is an example of your isotope. And of course that arrow is basically showing the electrons orbiting your nucleus. So I hope that is understandable. I know I'm going a bit fast, but I want to zoom through this part because it's very basic knowledge, which you should have known from GCSEs. If not, you should have remembered. So isotopes have similar chemical properties, but have... So isotopes have similar chemical properties because they have the same electronic structure. They may have slightly varying physical properties because they have different masses. Okay, so basically what they're trying to say is that isotopes have the same chemical properties because they have the same, because they have the similar nucleuses, but they have a different physical properties because, of course, you're increasing your nucleon number. So that's a bit understandable, but it's not something that you really have to know. It's more like common sense to understand that. So now we move to the important stuff, the time of flight mass spectrometer. Now that sounds like a big word, yeah, but it's not that complicated. I hope so. I will try to explain it the best way I can the best way I can physically explain it. I get mumbled with my words, of course. Sorry, I'm dead tired. Anyways, so I'm trying to move to your mass spectrometer, which is here. Now you will hear my laptop's fan currently. It's not a fan in the background, it's literally just my laptop fan, and that, when you hear that, I kind of panic a bit, so you might hear a change in tone in my voice because I'm like, holy shit, why is my laptop overheating? I paid good money for this laptop, it shouldn't be overheating. But yeah, that's just life, okay? I can't really stress about that. Anyways, so the time of flight mass spectrometer. Now, in these notes, they basically just give you the diagram. And they say the following are the essential 4 steps in the mass spectrometer. So they don't really give you a background of the mass spectrometer. Oh, no, they do. So the mass spectrometer can be used to determine all the isotopes present in a sample of an element to therefore identify elements. Wait, what? So the mass spectrometer can be used to determine all isotopes present in a sample of an element and to therefore identify elements. Okay, interesting. So the whole point of the whole point of the mass spectrometer is used to determine all the isotopes present in your element. So if we had taken hydrogen, for example, and we've taken a protium, your deuterium, and your last one, which I've completely forgot, and we put it through the mass spectrometer, the mass spectrometer would have detected if it was an isotope or not, and if any of the elements actually have that isotope. So that's interesting. So this will give you a better explanation. That's why I want to go through this first. So we can use the mass spectrometer to find out loads of stuff. It can tell you the relative atomic mass, the relative molecular mass, the relative isotopic abundance, and your horoscope for the next fortnight. Okay. So there are 4 things that happen when a sample is squirted into a time flight mass spectrometer. So it's TFO mass spectrometer, time of flight mass spectrometer. Okay. So I have to basically juggle between which one I should go through and which one I should teach. So what we should do is I'll read through this part. If we don't understand it, we'll go through this. That sounds like a plan. So let's go through everything in loads of detail and try to understand it, because I'm going to go through everything in just one go and just remember it and understand it. So the time of flight mass spectrometer. So the mass spectrometer can be used to determine all isotopes present in a sample of an element and to therefore identify elements. So the mass spectrometer can be used to determine all isotopes and elements. So elements can contain isotopes. So the whole point of the mass spectrometer, the main point of your mass spectrometer, is to find out the isotopic abundance, as we said here. So the amount of isotopes, and if there are any isotopes, which ones are there. So it helps us determine and find out if there are isotopes in an element itself. So it needs to be under a vacuum, otherwise the air particles would ionize and register to the detector. Interesting. So it has to be in a vacuum condition. The air particles would obviously go into the detection area, and your experiment would basically be ruined. So the following are the 4 essential steps in the mass spectrometer. So the ionization is the first one. So I'm guessing ionization takes place here because that's the ionization area. Of course it does. It takes place here. So ionization. So the sample can be ionized in a number of ways. 2 of these techniques are electron impact and electrospray ionization. Okay. The sample can be ionized in a number of ways. 2 of these techniques are electron impact and electron spray ionization. Oh, they don't actually explain all of it in one page. So they're doing 1, 2, 3, and then 4. Okay. I thought they were explaining all of that on one page. My apologies. Okay, that's fine then. So the ionization area, this is your first step of your time of flight mass spectrometer. The sample can be ionized in a number of ways. 2 of these techniques are your electron impact and your electrospray ionization. So you basically have to take your element and you have to ionize it, meaning you have to take electrons or give electrons to it to either give it a positively charged or a negatively charged. To make it a positively charged or a negatively charged particle. So electron impact. So a vaporized sample is injected at low pressure. An electron gun fires high energy electrons at the sample. This knocks out an outer electron, like I said, you either take or give, forming positive ions with different charges. So I think that's titanium. Do correct me if I'm wrong. No, that's not titanium because it's a gas. What is Ti? I should have a periodic table, to be honest. No, who the hell is that person? Titanium. Oh, I was correct. So, you have to be, okay, never mind. Of course you have to be in a gas state to go through the mass spectrometer, because they have to detect in the detection area. What am I saying? Apologies. So forming positive ions with different charges. So titanium goes through a mass spectrometer into the ionization area. A vaporized sample is injected at low pressure. So vaporized, I clearly missed that out. Vaporized meaning you've turned it into a gas. I don't know why they're using vaporized. They literally could have said a gas sample of your solid or whatever. But I guess it makes sense to say vaporized. So vaporized sample is injected at low pressure into your ionization area. So let's say here's your, could I draw on this? I actually can. Oh no, I cannot. Wait, I beg. Whoa. Sorry, how do I, that's completely wrong. Sorry, technical difficulties. How do I erase that? Okay, I can't erase that, I'm sorry. Oh, it's 100, sorry. I'm so confused, apologies. Oh no, I can do it here. Okay, let me get my stuff straight. So, is that a pen? Whoa, okay, that's a bit too thick. Sorry for the technical difficulties. Bear with me a sec. That's fine. No, yes. So vaporized sample is injected. Wait, I can delete this stuff. I'm sorry, I'm completely sorry. So vaporized sample is injected at low pressures. So a vaporized sample would look like this, let's just say, and it's a gas, of course. Whoa. So your vaporized sample is injected as a gas, okay? So this is technically your titanium, which is injected as a gas at low pressures through your ionization, through your basically time of flight mass spectrometer. It's a gas at low pressure. It is injected into your ionization area. So one of these is literally that. So let's just put that there, and let's actually make it smaller. Just make it more realistic. Okay. So an electron gun fires high energy electrons at the sample. So they're not really showing where your electron gun would be. So that's a bit annoying. Okay, they're not even showing here. So basically, if you can just imagine that electron gun might be here, and it's basically, what even? So let's just say that's an electron gun. Okay, let's move it down here. Let's just say that's your electron gun, and this electron gun is actually firing. An electron gun fires high energy electrons at the sample. Okay. So electron gun is firing high energy electrons at this sample. So this is our sample of vaporized titanium, which is basically a gas molecule that it goes through into our ionization area, which is injected into our ionization area at low pressure. Okay. So it goes through our ionization area. It's a vaporized substance of your titanium, and it goes through your ionization area at low pressures. Your electron gun fires high. Your electron gun fires high energy electrons at the sample. So that's your sample, which is in a gas form. Electron gun fires high energy electrons at the sample. This knocks out an electron. So if we do that, that's a small electron. Okay. So basically what happens is, oh, sorry. I know I'm repetitive, but it's the best way to explain it. So what happens is your vaporized element is injected into your ionization area using so your vaporized sample, not element. So your vaporized sample is injected into your ionization area. So your vaporized sample is injected into your ionization area at low pressures. So your vaporized sample is injected into your ionization area. Oh, why can I not move it? So your vaporized element is injected into the ionization area at low pressures. What then happens, let me just move here. What then happens is your electron gun fires high energy electrons at your sample. This knocks out an electron from your sample, and your electron is obviously taken away. Sorry. So this knocks out an electron out of your sample. So let's just say they put the electron there for safekeeping. So this knocks out an electron out of your sample. So this knocks out an electron out. It knocks out an outer electron out of your sample, and therefore forming a positive ions with different charges. E.g. titanium, which was a vaporized gas, becomes Ti plus your electron. There's many cool things in this, and I'm discovering them now, so I'm a bit slow at everything, but I've promised I'll get better. Let me just do it there. Okay. So I'm going to explain it one more time, and then I'm going to write it in a more simple and more compact and more, you can say, better way. So basically what happens, please do look at this, what I'm going to do, because it's the best way to explain it, to be honest. And I apologize for the sound that my laptop is making. It makes, I don't know why the fans have to work. I mean, I know why the fans have to work, so that they can cool down the PC, but I don't want my PC to be overheat. It stresses me out. Anyways, so we did say the sample can be ionized in a number of ways. So two techniques are electron impact and electron spray ionization. So this is the first way a sample is ionized in your ionization area. So the first way is your electron impact, which we're going through currently. So during electron impact, your vaporized sample is injected into your ionized. So during your electron impact, your vaporized sample. Sorry, I apologize for that. So during your electron impact, your vaporized sample is injected into your ionization area of your time of flight mass spectrometer at low pressures. So your let me just make that smaller. So your vaporized sample, I'm trying to move it. Let me fix that. So your vaporized sample is injected into your ionization area to be ionized by the process of electron impact, and it is injected at low pressures into your ionization area. Here, a electron gun fires an electron towards the here the electron gun fires an high energy electron towards the sample. So here's your electron gun fires a high energy So here your electron. I'm just making it bigger, just zooming in. Basically, I should have done this way before. So here your electron gun fires a high energy electron at your sample, causing an outer electron to be released. Doing so forms a positive ion with different charges. So your titanium, which was vaporized titanium, which is this. So your vaporized titanium is injected into your ionization area and goes through the process, is injected into your ionization area as vaporized titanium at low pressures and go through the process of electron impact. You'll hear an electron gun fires a high energy electron towards your sample, causing an outer electron to be knocked out and released, forming a positively charged ion of your vaporized titanium. So that's one way to ionize your sample. So time of flight, FLIGHT, mass spectrometer. And I know I will be repeating a lot of stuff. I will keep on going through it again and again, because some people actually learn by keep on reading something or keep on by repetition. If you're not those type of people, then you can clearly just listen to it once, then skip through to the part where I go to the next. If you are the type of people, this is the best way to study, is that you keep on repeating and try to understand it more than remember it. As long as you can understand it, you remember it fine. So the time of flight mass spectrometer. So let me accumulate a proper definition of the time of flight mass spectrometer. So the time of flight mass spectrometer So the time of flight mass spectrometer is a device, you can say, that is used under vacuum conditions. So the time of flight mass spectrometer is a device that is used under vacuum conditions. So vacuum completely wrong. Under vacuum conditions. And let me read the definition, sorry. The mass spectrometer can be used to determine all the isotopes present in a sample of an element and to therefore identify elements. So it identifies elements and identifies the samples in the elements that make up the element. So the time of flight mass spectrometer is a device that is used under vacuum conditions in order to determine, or you can say identify, in order to determine the isotopes found in samples of elements. I should just say elements instead of samples of elements. So the time of flight mass spectrometer is a device that is used under vacuum conditions in order to determine the isotopes found in elements. Now I know it then goes on with saying that in a sample of an element, therefore to identify the elements, but that isn't as important. And that's not the main job of your mass spectrometer. The mass spectrometer's main job in this situation, which they want you to learn, is that it basically allows you to determine which isotopes are found in your elements, or your samples of elements. So the time of flight mass spectrometer is a device that is used under vacuum conditions in order to determine the isotopes found in elements, or samples of elements or elements. So the first step, so there's four steps, 4 easy steps. So the 4 easy steps. The first one is ionization. So first one is ionization. So the sample is ionized in a number of ways. So 2 techniques of this is your electron impact and your electrospray ionization. So ionization is where your electron is ionized by 2 techniques. Apologies for the typos. So ionization is the first one. So ionization is where your electron is ionized by 2 techniques. Sorry, not your electron, your element / sample. Sample. So ionization is where your sample is ionized by 2 techniques. The first technique is electron impact spray. Not electron impact spray, the electron impact. During electron impact, so during electron impact, a vaporized sample is injected into the mass spectrometer. So during electron impact, a vaporized sample is injected into the mass spectrometer at low pressures and enters the ionization area. Here, I should just do it as one whole paragraph during that. So during electron impact, a vaporized sample is injected into the mass spectrometer at low pressures and enters the ionization area. Here, an electron gun fires a high energy electron towards our sample. This causes an outer electron. It's very important to say outer electron, because outer electrons are your valence electrons. That's a bit more detailed, so you don't really need to know what your valence electrons are. But if you do want to know, it's basically your valence electrons or electrons in your outer shell. So here, an electron gun fires a high energy. So here, an electron gun fires high energy electrons towards a sample. This causes an outer electron. To be released and ionizes our sample, giving it a positive charge overall. Right, that's very understandable. So during your electron impact, a vaporized sample is injected into the mass spectrometer. So during your electron impact, a vaporized sample is injected into your mass spectrometer at low pressures. Here it enters your ionization area, where your electron gun fires a high energy electron towards your sample. During contact or by contact, because the electron, basically what happens after it fires a high energy electron at your sample, this causes because it's electron impact, so I'm trying to fuse the title and the explanation together. It's literally electron impact. So the electron impacts onto your sample, causing the outer electron to be released. Therefore, ionizing your sample into a positively charged sample. I hope that's understandable. So forming a positive ions, different charges. So your titanium in this case, this is your titanium sample, which is vaporized into your positively charged ion of titanium, and then an electron is released. So it says the electron impact is used for elements and substances with low formular mass. Electron impact can cause larger organic molecules to fragment. So the electron impact is also used, so it's used for substances with low formular mass, but it also can be used to allow large, so it can also be used to allow larger organic molecules to fragment, to basically break apart or like break into small pieces. So I hope that's understandable. So now electron spray ionization. So of course there's two types of ionization: your electron impact ionization, and your next type is your electron spray ionization, electrospray ionization. And of course, as we said, our definition of ionization is where your sample is ionized by two techniques. The first one is your electron impact, and now we're going to go through your electrospray ionization. So during the electrospray ionization, the sample is dissolved into volatile polar solvents, now injected through a fine hypodermic needle, giving a fine mist or aerosol. The tip of the needle has a high voltage. So at the tip of the needle, the sample molecule M gains a proton, which is H+, from the solvent forming MH+. So M, which is in your vaporized form, combined with the hydrogen, which is your proton, to give you MH+. Okay, interesting. So the solvent evaporates away while the MH+ ions move towards a negative plate. So, okay, that's interesting. So instead of actually gaining electron, instead of actually ionizing the sample itself, what it does is it gives the sample a proton in order to ionize it. So in the electron impact, it gives you your electron. But in your electrospray ionization, it gives you a proton. Oh, I should have done that all at once. Now we're going to go through the electron spray impact in detail, of course, but I want to know what this is saying. So the sample is dissolved and pushed through a small nozzle at high pressure. A high voltage is applied to it, causing each particle to gain a hydrogen ion. The sample is turned into gas and made up of positive ions. Okay. So electrospray ionization. The sample is dissolved in a volatile polar solvent, injected through a fine hypodermic needle, giving a fine mist or aerosol. So it gives you a good smell, I guess. So the tip of the needle has high voltage. At the tip of the needle, the sample molecule M gains a proton, which is your hydrogen ion, from the solvent forming MH+. So the solvent evaporates away while the MH+ ions move towards the negative plate. Now I feel like they've complicated this a bit too much, and they didn't have to mention big words like volatile and polar solvent and all of that. So let's go through this, okay? Because I wanna explain in the best way possible, not in the most complicated way. Because as long as you understand it, that's the most important thing. And before I do go through this, I want to see what the textbook is talking about. Because if the textbook does give a decent understanding and a decent explanation, then that's completely fine. So your mass spectrometer is page 27. Now I don't really encourage the use of the textbook, because the textbook to me is more like something the teachers can use if they need help. But because the textbook doesn't... Oh, sorry, I think I just opened my messenger. I wasn't really meant to do that. No, where have I gone? Here. Fam. Oh my god. Yes, I know I have my hotbar there. So let me just move that to here. Okay. So the electron spray ionization. So in this method, the sample is dissolved in a solvent and pushed through a small nozzle at high pressure. A high voltage is applied. Oh, it's literally the same definition as your as your CGP revision guide says. Okay, let's just use this definition then. So in this method, the sample is dissolved in a solvent. So your vaporized sample is dissolved into a solvent and is pushed through a small nozzle at high pressure. It makes sense why it's at high pressure, because it's pushed through a small nozzle, therefore multiple particles are trying to go through that small nozzle, therefore there's high pressure. So in this method, the sample is dissolved in a solvent and pushed through a small nozzle at high pressure. A high voltage is applied to it, causing each particle to gain a hydrogen ion. The solvent is then removed, leaving a gas made of positive ions. So in this method, the sample is dissolved. The sample is dissolved in a solvent and pushed through a small nozzle at high pressures. Wait, okay. I was going to pause and try to decrease the volume of the thing in the background. Of course, it's Quran, and I don't really want to do that, but it's kind of never mind. So electrospray ionization. In this method, the sample is dissolved in a solvent and pushed through the small nozzle at high pressures. A high voltage is applied to it, causing each particle to gain a hydrogen ion. The solvent is then removed, leaving a gas made with positive ions. So basically, so let me delete our electron gun and our excuse of a electron itself. Oh, I thought that was electron gun. I'm like, bruh. Anyways, so this is our sample. Basically, during electrospray ionization, our vaporized sample goes through and into our ionization area. Okay? Here what happens is it's dissolved in a solvent, and that solvent is actually, it's dissolved in a solvent. Sorry, let me read it again. I'm wanting to explain it the best way possible, not the worst way. So this is basically the sample is dissolved in a solvent and pushed through a small nozzle at high pressures. A high voltage is applied to it, causing each particle to gain a hydrogen ion. So a high voltage is applied to it, causing each particle to gain a hydrogen ion. The solvent is then removed, leaving a gas made up of positive ions. Sorry, give me a sec. So in this method, the sample is dissolved in a solvent and pushed through a small nozzle at high pressure. High voltage is applied to the solvent, causing each particle to gain a hydrogen ion. The solvent is then removed, leaving a gas made with positive ions. Okay. Bro, why does everyone have to make fucking noise now? Holy shit. Okay. So electrospray ionization. So during electrospray ionization, your sample is first dissolved into a solvent and is passed through a small nozzle at high. So during electrospray ionization, your sample is first dissolved into a solvent and is passed through a small nozzle at high pressures. So during your electrospray ionization, your sample is first dissolved into a solvent and is passed through a small nozzle at high pressures. So in this, it actually talked about a needle, and that's what is kind of confusing me, because that's talking about a needle, the other thing's talking about a nozzle. So I just want to get the best understanding of it. So a solvent is pushed through a small nozzle at high pressures. A high voltage is then applied to your solvent or your nozzle. They're not detailed enough. It's annoying. So a high voltage is applied to it, causing each particle to gain. So high voltage is applied to it, causing each particle to gain a hydrogen ion. The solvent is then removed, leaving a gas made up of positive ions. Okay. So basically, a high voltage is applied to your solvent. So during electrospray ionization, your sample is first dissolved into a solvent and is passed through a small nozzle at high pressures. A voltage is then applied to this solvent, giving each particle a hydrogen ion. So voltage is then applied to the solvent, giving each particle a hydrogen ion. This concludes... sorry, I haven't finished. The solvent is then dissolved, leaving us with the solvent is then dissolved. The solvent is then dissolved, leaving us with vaporized. I like the word vaporized. Leaving us with a vaporized sample. Vaporized ionic sample. I want to say ionic, what is that? Vaporized ionized sample. Yeah. Okay. So during the electrospray ionization, your sample is first dissolved into a solvent and is passed through a small nozzle at high pressures. A voltage is then applied to your solvent, giving each particle a hydrogen ion. The solvent is then dissolved, leaving us with a vaporized ionized sample. So let me try to explain on this diagram. So let me do some adjustments to this. I'm on pen mode. So when you look at this, ignore this, ignore this, ignore this, ignore this. So basically ignore everything I'm crossing over. Because that's in the detail which is not needed. I'm not going to do another cross stitch because that's just wasting time. So in this case, our sample is M. We have a vaporized sample of M. I believe M is what you usually use in order to explain what a sample is. And I don't think M is actually an element. Not table. Yeah. Is it actually an element? I don't think it is. What is M element? Yeah, it's not. Yeah, I was right. Alhamdulillah. So it's not actually an element. They basically use M as an example of an element. They do it a lot. So they might ask you a question like, oh, M goes through the process of electron impact and electrospray ionization. Explain how M goes through these two techniques in order to ionize M. Now they might not give you that simple or basic a question. If they do, it's actually a decent question to answer, and it's actually easy 4 markers. But they most probably won't actually give you a question like that. But if they do, just understand that M is not actually an element, so don't go on the periodic table looking for M. It's just an example. Anyways, so during your electron spray ionization, now I'm going to explain why I said proton in a bit, because hydrogen is actually because it's H+, so H+ is a proton. I know I said in a bit, but I just explained it. So basically, you can't really see on this. Let's say that's your solvent, okay? Say this whole thing. I want to draw a circle around it. I don't know. Oh, it's not a see-through circle. Send backward. Send back. Oh, it makes some difference. Anyway, so this whole thing is your solvent. So you're vaporized. So during electrospray ionization, your vaporized solution, your vaporized sample, is dissolved into a. Let me actually do it on the side because you can't really see it here. So let me make multiple things like that and then like that. Okay. Wait, how do I change the color? I know this is not important, but it just makes life so much easier. Oh, I can write in it. Whoa, okay, that's pretty cool. So I'm gonna write S for solvent, because I can't really show you the difference. And in this I'll write S for solvent, okay? How do I make it? Okay. Oh, you can't even see the S, wow. That's useful. Okay. How do I straighten? Okay, I can't really straighten it. So during the electrospray ionization, your sample is ionized by first being dissolved in a solvent substance. So during the electrospray ionization, your sample is your vaporized sample is first dissolved in a solvent. Sorry. So during your electrospray ionization, your sample is first dissolved in a solvent. Basically, what that happens is I'm trying to find the best way to do this. Okay, let me do it like this, and then let's make that your nozzle. Okay, so during electrospray ionization, your sample is dissolved into your solvent. Please let me just grab it. Okay, so during electrospray, why does it have to increase when I'm explaining something? So annoying. So during your electrospray ionization, your sample is dissolved into your solvent. Here it goes through a small nozzle at high pressures. It then goes through a small nozzle at high pressures, and here it goes through a small nozzle at high pressures where a voltage is applied to the sample. This voltage gives the sample a proton. This voltage gives the sample a proton, which basically attaches to the sample, forming. I'm explaining the worst way. I apologize. So during electrospray ionization, your sample is first dissolved into a solvent and is passed through a small nozzle at high pressures. So during your electrospray ionization, your sample is dissolved into a solvent and is then passed through a small nozzle at high pressures. A voltage is then applied to the solvent, giving each particle a hydrogen ion. The solvent is then dissolved, leaving us with our vaporized ionized sample. So during electrospray ionization, sample is dissolved into our solvent. So during electrospray ionization, our sample is dissolved into our solvent, and which then goes through a small nozzle at high pressures. It is then a voltage is then applied to causing the particles. Voltage is then applied to the solvent, causing each particle to gain a hydrogen ion. The solvent is then dissolved later on, leaving us with a vaporized ionized sample. So this is a vaporized ionized sample. So your sample is first dissolved in a solvent and goes through a small nozzle at high pressures. Here a voltage is then applied, causing each particle to gain a hydrogen ion. The solvent is then dissolved, leaving us with a vaporized ionized sample of MH plus. So the solvent evaporates away while MH plus ions move towards a negative plate. So that's basically talking about the progress of everything else. Okay, so I know I'm taking time, but time is important. And what I want to do is that I want to make... Okay. Bear with me a second because I want to try to make it so that I give my laptop enough rest at the same time, but at the same time I study well and explain it well. So I think the minute... Okay, so let me just explain it to you guys because you guys are here anyways. So that's 1, 2, 3. How do I go? So there's basically 9 pages. The minute we complete 9 pages, I will give my laptop a break. I know there's loads of other parts of this topic, but I want to give my laptop a break because I don't want to overheat my laptop and eventually destroy it because it's not worth it. As much as A levels are important, it's not worth it. Anyways, So we've talked about our first ionization. Our first step, our first process, our first step in your time flight mass spectrometer, which is your ionization, where electrospray and electron impact takes place. So as we know, during electron impact, what happens is your sample, your vaporized sample, goes through your vaporized sample enters your ionization area at low pressures. Here, an electron gun fires a high energy electron at your sample, causing the outer electron to be released, making it become into a ionized sample, which is positively charged sample. The next technique is your electrospray ionization. During electrospray ionization, your sample is dissolved into. During electrospray ionization, your sample is dissolved in a solvent, which then goes through a small nozzle at high pressures. Where the voltage is then applied, so each particle gets a hydrogen ion. Eventually, your solvent then evaporates, leaving us with a vaporized, ionized sample. I think a miracle has happened. My fan stopped. Okay, that's fine. Alhamdulillah, my fan stopped. I mean, it's a good thing because I don't like making you. If you like, you will understand. I love this laptop. Anyway, so the next thing is your acceleration. The next step is acceleration. So acceleration, the positively charged ions are accelerated by an electric field, so that they all have the same kinetic energy. This means that the lighter ions will end up moving faster than the heavier ions. Okay. Where am I? Yeah, here. Oh, not here. Fam, how do I... Fam. I swear to God, bruh. Just want to go to the second page. So acceleration, the positive ions are accelerated by electric fields to a constant kinetic energy. So K equals half times mass. Oh, this is a different equation. Is it? So K equals half times mass. Oh no, it's the same. It's missing. I thought that was an N. Yeah, there you go. You're welcome. So K equals half times mass times velocity squared. So during acceleration, which is the second process, I'm most probably going to remember this and explain this one because it's easier to remember than the other one. So during acceleration, the positive ions are accelerated by an electric field with a constant kinetic energy of K equals half times mass of velocity times velocity squared. So K is kinetic energy of the particle, which is in joules. As we know that all energy is measured in joules. Mass of the particles in kg, and velocity of the particles ms minus 1. So rearrange gives us v equals square root of 2 ke divided by m. Oh, so they would want us to calculate the velocity of your positive ions. Interesting. So given that all particles have the same kinetic energy, the velocity of each particle depends on its mass. The lighter particles have a faster velocity and the heavy particles have a slow velocity. And that's basic common sense. So even though during acceleration the positive ions are accelerated by electric field and are each given a constant kinetic constant kinetic energy, even though that is true, the lighter positively charged ions will move faster than the more heavier positively charged ions, and that's just life. So you do not need to learn these equations, but may be asked to rearrange them and use them in a calculation. See, that's what I love about these notes, is that they give you exam techniques, fam. So, oh, that's lovely. So they're saying that you don't really need to know this equation, but they may be asked to rearrange in the exam. So they might just give you this equation, and they might be like, oh, Bob wants to find the velocity of Bob wants to find the difference of velocity between the light and heavy positively charged ions. Which equation should he use and how should he apply his which equation we should use. So basically you just have to say, okay, K equals half times mass and velocity squared. You just have to then rearrange it into velocity equals a square root of 2 times Ke divided by m. So now most probably they will just ask you about this equation. They would want you to rearrange it most probably into this equation. I don't know why I'm doing it, because I know it covers it, but I'm still doing it anyways. So they most probably want you to rearrange it into this equation. So just remember this one. So V equals 2Ke 2Ke over m. So that's understandable because the half is time. So half is times there, leaving you with 2 times Ke. Fam, I suck at math. I'm not even gonna try. Alright, so that's calm. So acceleration is the next. Acceleration. So acceleration is the next process. So during acceleration, why did I write electro? During acceleration, the positively charged ions are. So during acceleration, the positively charged ions are passed through. Or did they give it a name for the area? Because they're just giving everything a name. Let's be honest. Oh, wrong. Fam, I was there anyways. Fam, where am I going? Yeah, acceleration area. Lovely. So during acceleration, the positively charged ions are passed through to the acceleration area where they enter an electric field. Here they all gain constant kinetic energy, but of course lighter positively charged ions move faster than the heavier positively charged ions. Now guys, do bear in mind, I don't know why I made that mistake. Now guys, do bear in mind that I know the basics of this. So I am a bit rusty myself too. So when I'm going through this, I'm actually teaching myself and explaining it to myself and understanding it myself. So don't be like, oh, this guy knows everything and I know nothing, fam. Like, bro, what did he do? Let's just ask him. I did nothing. I have done 0 revision at all. So don't look at me and be like, wait, let me just look at my phone. Don't look at me and be like, yo, this guy knows his stuff. I do not know any of my stuff. I'm going through it right now with you. So if you feel like you're very close to the exam and you've effed up because you haven't studied anything and you're like, okay, I'm literally doomed, don't think like that, fam. I got you, yeah. We're in the same situation, both in the same boat, yeah. So it's blessed. So we went to the first one, which is ionization. Now we go to the second one, which is acceleration. During acceleration, what happens is that your during acceleration, your positively charged ions are passed through into your acceleration area and enter an electric field. This electric field gives oh, please don't tell me that paused my recording, because it did last time. I'm gonna pause it now.